I'm very happy to be here, and we thank you. So today I will talk about three-dimensional gravity, especially Chern-Simon's gauge theory formulation of three-dimensional gravity, and then I will address how to accommodate this Thurston geometry in this context. This work is based ongoing work with my students. So today I will review the underlying physics. Maybe I cannot report our result. Maybe stay tuned. Maybe if I finish this work, then I will report our result. Okay, so let's count the number of independent components of Riemann curvature tensor in d dimensions. So we have to consider first Bianchi identity, because first Bianchi identity gives us the linear relation between Riemann curvature tensor. Then we can count the independent component, and then we have this number. And then Riemann tensor consists of two components. One is the Weil tensor. Weil tensor is a traceless component of Riemann tensor, and then trace part is Ritz tensor. Okay. And then we can count Ritz tensor, then remaining is Weil tensor. So if we consider 4 dimensions, then number of Riemann tensor is 20, and then this 20 is split into Ritz tensor, 10 component, another Weil tensor, 10 component. And in some sense, 4 dimension is special, and this is the only dimension with number of Riemann tensor equal to number of Weil tensor. Also, in 4 dimension is special in that sense. We have this group or SO2, 2, and then this is the only semi-simple group. If we go to higher dimensions, then Lorentz group becomes simple group. And this splitting is actually very interesting because it is related to the instanton structure and the chiral fermion eventually. And then this Weil component is described by this self-dual equations. It is called gravitational instanton. And then this Ritz part is described by famous Einstein equations. And as I mentioned, this SO4 is split a double copy of SO2. And then the splitting is deeply related to the self-dual structure of two forms. So self-dual structure of two forms appears in gravity and the gauge theory. And there is a deep relation between Yang-Mills instanton and gravitational instanton. And if you consider this equation without matter, that solution is called Einstein manifold, described by this equation. It turns out that if you use this structure, then Einstein manifold is actually a composite of gravitational instanton and anti-instanton. But as I mentioned, if you use gauge theory formulation of this object, then the self-duality may actually a Yang-Mills instanton, because a spin connection can be regarded as a gauge field of a Lorentz group. Then this object in the gauge theory language is a Yang-Mills instanton. So we have two kinds of Yang-Mills instanton. SU2 plus belong to this group, and then SU2 minus instanton, that is anti-instanton. They have opposite self-duality structure. And also, 3 dimension is also interesting because the number of Riemann tensor is 6, but it is equal to number of Ritz tensor, right? T equals 6, then we have 6 component. So, this dimension is special in this sense. So only dimension with number of Weil tensor becomes 0. In other words, number of Riemann tensor is equal to Ritz tensor. That means there is no true gravitational degrees of freedom in 3 dimensions. And also, 3 dimension is also special because the gauge field field strength is 2 form, and then the hot GDR is 1 form. Then 1 form has the gauge field in terms of scalar field. So there is a duality between gauge field and scalar field. And then this structure is deeply related to the dot invariant. So as I mentioned here, the number of Riemann tensor is equal to the number of Ricci tensor. So in 3 dimensions, Riemann tensor is completely determined by Ricci tensor and Ricci scalar. So if you require a vacuum solution of Einstein equations, then in 3 dimensions, only solution of Einstein equation is just the constant curvature space. Physically, this means that on 3-dimensional Einstein space-time, there is no local propagating degrees of freedom. So theory is essentially topological. Maybe we may address D equal 2, but we cannot apply this formula for 2 dimensions because in order to count this number, we used first Bianchi identity. First Bianchi identity, we consider these 3 indices, but it's completely anti-symmetric. So in 2 dimensions, this Bianchi identity becomes trivial. So actually, in 2 dimensions, the number of Riemann tensor is 1. If we just believe this counting, but Ricci tensor is 3, right? So ridiculous. So we should not use this number for D equal 2. Also, but in 2 dimensions is interesting because this Einstein action is basically topological, related to Euler characteristic. I mean Euler number of some surface, and G is the genus of this surface M. If you consider Riemann surface, then G is the genus of Riemann surface. And so in order to describe some non-trivial gravitational theory, then we have to deform this theory by including this dilaton field. And also we have to consider boundary term. And then this action is recently popular because it is related to Jacob-Teitelbaum gravity. Where here, this Claudio Teitelbaum is very famous physicist. He also appears in BTZ, but he changed his name in 2005, and his new name is Claudio Bunster. He wrote many papers with this name. I heard some sad story about this. Anyway, so as I just mentioned, 3-dimensional gravity has no local propagating degrees of freedom. So theory is basically topological. And the surprise is that there exists precise equivalence between gravity and gauge theory in 3 dimensions. And the 3-dimensional gravity should also be topological, right? Because there is no local propagating degrees of freedom. Then what is the corresponding gauge theory of 3-dimensional gravity? Well, there is a well-known topological gauge theory in 3 dimensions, that is Chern-Simons gauge theory. So this is topological. So this theory has d homomorphism symmetry, also gauge symmetry. And if you have this kind of Chern-Simons gravity, then depending on your choice of gauge group, you can accommodate several spaces, okay? For example, if you consider SO4, then the underlying space becomes S3. ISO 2,1, then we have asymptotically flat space-time, but SO 2,2, then we have famous ADS3 gravity with this negative cosmological constant. So in order to accommodate 6 component, I mean, in 3 dimensions, we have 3 dry binds and 3 spin connections. And then we have length 6 gauge group. But of course, if we consider product space, I will introduce Thurston geometry. Some of Thurston geometry is product space. In that case, we need a smaller group. Actually, we have three spaces with length 6, but we have mostly the length is 4 or 3. I will show you later. So, but I want to focus this anti-digital space because it is related to holography. I mean, this is three-dimensional gravity theory. Then it has boundary. Boundary is the two-dimensional conformal field theory described by Bess, Jumino-Witten, or rebuild theory. And there are many important works regarding to this ADS3. Well, this ADS3 is realized as some embedding space in this R2, 2. So we have two time directions. The embedding condition for this ADS3 is given by this one. So the underlying isometry of ADS3 is SO2, 2. You can easily see oh, sorry. The typo, this must be minus. Well, if we just consider Euclidean digita, then well, we have a plus sign, but so this is typo, sorry. So the isometry of this space is SO2, 2. So we have this Lorentz algebra. And then we can introduce most general killing form, I mean the non-vanishing trace. Of course, this trace must be non-degenerate, and then the most general structure is given by this. The interesting thing is this new term is allowed because if we consider SO4 or SO2, 2, some underlying space is R4, and then this is R2, 2 for ADS3, and then this space allows self-real structure, real self-real structure. But if we consider SO3, 1, then self-real structure becomes imaginary. And this self-real structure is related to the instanton structure. And this self-real structure acts on this generator, Lorentz generator. In some sense, Lorentz generator corresponds to the two forms. There is a famous Clifford isomorphism between X algebra and Clifford algebra. And this self-real structure acts on this, like this. And then you can easily check the self-real structure. I mean, the square is just 1. So this we can introduce a projection operator using this property. And then P plus, eigenspace of P plus is called self-dual. And then eigenspace of P minus is called anti-self-dual. And then in terms of component, this projection operator is given by this. And then we'll use this projection operator to split this Lorentz generator into plus part and minus part. So we define chiral generator using this projection operator. And then you can easily check this plus, minus, I mean, chiral generator separately satisfy Lorentz algebra, and they are commuting each other. And then this previous killing form can be reduced to this one for chiral generators. So we have mu and mu is just mixed together in this chiral generators. And then let's split this Lorentz generator for ADS3 because we want to describe ADS3. And then minus 1A, that is A is now 0, 1, 2, three-dimensional index. That becomes translation generator, and then this JAB becomes Lorentz generator in three-dimensional space. And we choose this orientation. And then the previous Lorentz algebra becomes this one in terms of this PA and JA. And then the killing form has this structure. So PP is characterized by U coefficient. And then PJ is realized with new coefficient. And the reason why we should have this non-generate pairing is due to the existence of Pauli-Lubansky form. In Pauli-Lubansky, in 3 dimensions, become not vector, just scalar. So we have this non-trivial killing form in 3 dimensions. In terms of this P and J, this chiral generator becomes this one, and the momentum generator becomes this one. And we have this algebra. I already introduced this one. Okay. Then let's define SO2,2 connection to define Chern-Simons gauge theory. Well, SO2,2 connection is defined by this one. JAB is a previous Lorentz generator. But in 3-dimensional language, this 1A, that is dry bind. And then omega AB, because this is a PA, and then the corresponding gauge field is dry bind. This is the rotation generator in 3 dimensions. So corresponding gauge field is spin connection. So we can accommodate dry bind and spin connection together into this SO2,2 connection. But in terms of chiral generators, this 2,2 connection is split into this form. So A plus and A minus is a positive chiral gauge field and negative chiral gauge field. But here, because this A-2,2 is the underlying space of A-3, but A-3 has cosmological constant lambda, so 1 over L square, and L is basically the radius of A-3. So in order to recover this parameter, we need to scale this dry bind is scaled like this. And then the momentum operator also scaled like this, but then we don't have any change here. Then we can explicitly recover this cosmological constant. Then this algebra with this new momentum generator becomes this one. And then if you take a large L limit, then PA, PB is commuting each other. So we recover ISO2,2 from this SO2,2. Okay, if we take this large L limit. And then now we are doing some related work to understand some flat space holography. This is ongoing collaboration with Professor Berman-Lee and then Tabassum and Patricio. But this is not my subject today. Okay, then let's define curvature. The curvature is this is the dA, and then we gauge with non-abelian, so we have this nonlinear coupling. And then if we just use this one, this structure, and then we have this expansion for this two-form curvature. This R A omega is actually a curvature tensor of spin connection, and this TA is a so-called torsion. Okay, so the corresponding field strength of momentum generator is torsion, and then the field strength of rotation generator is curvature, but we have this structure because of we have ADS3 with cosmological constant. Actually, cosmological constant is coming from this term. So if we just evaluate the Chern-Simons action, this is basically topological, and then we have this term. And then we have, of course, we need integration by part to derive these equations. So we have boundary term. But in this theory, boundary is important. We have to keep this one. I mean, in gravity theory, the boundary term is called Gibbons-Hawking term because every physical information actually encoded in the boundary. So we need to carefully keep this boundary, or we need this boundary term to make a connection with two-dimensional conformal field theory. Anyway, the bulk theory is trivial, right? Because equation of motion is this one. So the field strengths just identically vanish. That means, well, this is consistent with the result. In 3 dimensions, there is no dynamical degrees of freedom, topological theory. So the solution of this equation is just the pure gauge, okay? But if we use this pure gauge for boundary theory, then boundary theory induced Bessel-Zumino-Witten term, and the Bessel-Zumino-Witten term by Hamiltonian reduction, then we have rebuilt conformal field theory on the boundary. And then let's look at the equation, because the curvature tensor is given by 2 components, this one and this one. So equation of motion is this one. So we'll have this term vanishes, also this term vanishes. And then the first equation, well, this is the torsion precondition. So we'll recover Einstein gravity. In order to recover Einstein gravity, we have to impose this torsion precondition.
So here you took the large L limit already? Or
no.
The finite?
Yeah, the finite. And then this is the Einstein equation. I will prove this, this statement. So in 3 dimensions, we can use this epsilon tensor, and then using this epsilon tensor again, then this Riemann tensor can be written in this way. And then if we use this result for this, this is the curvature tensor of spin connection. And then this is the actually cosmological constant term. So if we just insert this result here, and then the final result of this equation becomes this one. So this is a precisely Einstein equation with negative cosmological constant. So this is a really Einstein equation.
You put L equal 1 or?
Sorry?
1. 1. Where is it?
Sorry?
Small L is 1.
Small L? Yeah. At this stage, I don't rescale. But in order to recover this cosmological constant, then we need to scale this one. But here I will use this one. But in order to have explicit cosmological constant, then I have to recover this parameter L. Okay, then this result also confirmed by calculating the action explicitly. And then we have a very funny situation. So if we expand with also very general killing form, then we have 2 terms. So one is the mu term, and this is a Chern-Simons functional. This is the spin connection is given by this one. And then we have torsion part, but we have new terms because killing form allows this new term. And then we have this one, and then of course boundary term. But in terms of chiral gauge field, this Chern-Simons action split into 2 parts. So positive chiral and negative chiral field. And Chern-Simons density for the chiral field is given by this one.
But the usual Chern-Simons theory used to have the gauge anomaly, but how about that?
Yeah, good question. So actually, if we allow this mu term, then there is an anomaly, gravitational anomaly.
The end of the expression, I think the gravitational anomaly, the gauge anomaly for the A plus and A minus should cancel.
But actually, if we consider only mu term, that is the that is the left-to-right symmetric. So anomaly is cancelled. But if you allow this mu term, then no cancellation.
So if we allow the mu term, then we are not recovering the usual Einstein-Hilbert action.
No. But it's a funny situation. Okay, I will explain. Thank you for your question. So, for example, if you just put mu equals 0, then if you just evaluate dry bind, that gives rise to Einstein equation. But spin connection variation gives you torsion precondition. But if we choose nu equals 0, then this is gone, and then we have this gravitational Chern-Simons coupling. And then the situation is the opposite. If we evaluate dry bind, that gives you torsion precondition. But if you evaluate spin connection, that gives rise to Einstein equation. But if you allow both terms, then according to Witten, this theory describes topologically massive gravity with gravitational Chern-Simons coupling, this one. But this is very similar to Maxwell Chern-Simons, because here the number of derivative of metric is 2, right? But here, because this contains omega is a spin connection, right? So this term has higher derivative than this. So one more derivative. So this is very similar to the situation in Chern-Simons, and if you consider Maxwell, then Maxwell theory has one higher derivative. And then according to Desert, Jacob, Templeton, if we include this one, then there is a propagating degree of freedom. Spin to degree of freedom, which is propagating. It's very similar to Maxwell Chern-Simons. If we consider Maxwell Chern-Simons, there is a massive photon, and then similar situation happens. But I think so in that sense, this is interesting. But of course, anomaly issue is serious. But as far as I know, there is no serious work about the holographic aspects of this theory with this mu term. And because there is a bulk degree of freedom and propagating spin to mode, so holography may be not trivial. But I think interesting problem.
Do we set mu and nu as integers?
No, actually, this level is quantized. Then there is constraint. Actually, this mu, if you just impose the quantization condition, then mu and nu may be the integers. And but I want to ask the following questions. Actually, that my question is mostly raised by Witten in this paper. So three-dimensional gravity is really equal to gauge theory? Well, maybe the answer is maybe not. Why? In Chern-Simons gauge theory, dry bind may be not invertible, because in classical, in Chern-Simons gauge theory, this kind of solution is allowed. A equals 0, E equals 0, E equals 0 means there is no space-time, okay? But in order to complete a path integral measure, and Witten's claim, we have to include this one. But it is not allowed in gravity theory, right? And the symmetry of gauge theory is actually larger than gravity, because Chern-Simons gauge theory has diffeomorphism, also gauge symmetry. So symmetry, underlying local gauge symmetry is not matching. And then there is also issue in quantum gravity. We know we have to need topological sum, right? We have to include all kinds of topological category of three-dimensional manifold. Then the question is, what is the meaning of topological sum in Chern-Simons gauge theory? It's not clear. Also, three-dimensional gravity is topological. So all physical informations are encoded in boundary and topology. And then what is the corresponding information of this topology and boundary condition in gauge theory? Also, this topology and boundary conditions are matched together? It's not clear. Also, in gravity, we know that black hole solution exists, right? And then this so-called BTG black hole. And BTG black hole has finite horizon, also finite Bekenstein Hawking entropy. then there's a question. So if three-dimensional gravity, including this black hole solution, is equal to gauge theory, this gauge theory, Chern-Simons gauge theory, then is it possible to accommodate the huge degeneracy of this Bekenstein-Hawking entropy in Chern-Simons gauge theory? Maybe not, because topological theory only allows few degrees of freedom, right? But we believe, I mean, this at least for this ADS3, we have holography. So all this information, topology, I mean, at least these boundary conditions is related to two-dimensional conformal field theory. Then the question is this topology and boundary conditions are not determined by underlying action, right? Topology and boundary conditions are determined by problem solver, right? You choose specific topology and you just impose boundary conditions. So everything is there, at least three-dimensional theory. And my question is, what is the physics? Well, I think the holography is not an answer, because even in two-dimensional theory also depends on boundary condition, also the topology of Riemann surfaces. So I think this relation is not clear. And this is the viewpoint, not my viewpoint, Witten's viewpoint. He published this one only archive, but citation is almost 900. So very beautiful paper. Okay, but at least if we believe some correspondence between Chern-Simons gauge theory and three-dimensional gravity, and then the topology or shape of three-dimensional manifold depends on your choice of gauge group. As I already mentioned, for maximally symmetric spaces, this H3 we call ADS3 and S3. This is the three-dimensional Digita space, and then this is the Euclidean space. That is a maximally symmetric spaces. Then we have length 6 gauge group. But other space, I mean, I will introduce Thurston geometry. Thurston geometry has 8 kinds. So this is very familiar, and this one is product space. And then we have some strange space. I will explain a little bit. And then this space, for example, this is a product space, then length is smaller. So for example, let me show the result first. So E3, S3, H3, that is the maximally symmetric space. Then the corresponding gauge group is length 6. But this is the product space. Then the length is 4. Only 4 generator is enough to describe this space. And then this Neal space, solve space, SL2R, that is this, the number of generator is 4, 3, 4, okay?
But did you need the dimension of the Lie group, not the rank of the Lie group?
Dimension of Lie group, sorry. Dimension of Lie group, sorry. So in this case, the choice of gauge group in Chern-Simons gauge theory is related to the topology of 3 manifold. Then the question is, can we have some classification of 3 manifold? Then yes, that is Thurston conjecture, and the Thurston conjecture is proved by Perelman. According to Thurston conjecture, 3 manifold with given topology has a canonical decomposition into connected sum of simple 3 manifold. That is 8 kinds. So H3, the physicists, we say this is ADS3, this is Euclidean Digita, S3, and then Euclidean space, and then it's the product space, and then we have some strange space, and then this geometrization conjecture by Thurston, famously proved by Perelman. He introduced very interesting theory. I will briefly introduce Perelman's result. This Neal space, Neal geometry is associated Heisenberg group is given by this one. So basically some translation generator. And this space is twisted, but not negatively curved. And this nil geometry appears some torus bundle. And but the strange thing is distances behave anisotropically. So different directions scale differently. And the solve geometry has this strange metric. So if you just look at x direction, that is expand, right? But if you look at y direction, it shrink, right? According to this dimension G. And this solve manifold arises also torus bundle with hyperbolic monodromy. And then this is the SL2 group manifold, SL2R, because SL2R has 3 generators, and then this is the manifold. So define 3-dimensional manifold. And of course, this space is defined by universal curve of SL2, R, and famously related to the hyperbolic geometry. And then this geometry also appears in Seipert fiber space. Seipert fiber space, just locally looks like this one. So we have some surface, and then we have circle. That is the local structure of this Seipert fiber space. And this space is one of the most technically sophisticated geometry. Still, mathematicians are working on this manifold. The isometry also non-trivial. I showed already this. And then in this space, this 3 space only Einstein manifold. And the others, not Einstein manifold. That means only this 3 space is just solution of Einstein gravity. This is not Einstein manifold, so Rich tensor usually non-vanishing. That means we need matter, right, to describe this kind of geometry in the context of Einstein gravity. But one can construct a 3-dimensional Chern-Simons gauge theory in which each gauge group is the group of isometries of given Thurston geometry. And then, as I mentioned already, this is the isotropic geometries. And then this 3 space is the solution of pure Einstein gravity, but the others are not Einstein. And then the local metrics are known like this. But the interesting question is the following. This is there is also Lorentzian version of Thurston geometry, and then the interesting question is where we can modify our gravity theory. For example, we can include this higher derivative term introduced by Townsend and called the new massive gauge theory. So this this gravity theory contains higher derivative described by this K tensor, and then listen to what show that all these 8 geometries can be a solution of this equation. Okay, so this new massive gravity can accommodate all 8 Thurston geometry as a vacuum solution. And then the underlying action is given by this one. So this is the usual Einstein gravity. And then we have this higher order terms. The higher order term is R square and then Ricci square, Ricci scalar square. And actually this Perelman's theory, in order to describe this uniformization theorem, I mean, we have 3 manifold, and then if we wait long time, then the geometry becomes smoothing, and the smoothing procedure is described by this flow equation. This is so-called Hamilton's flow, but this Hamilton's flow is very similar to heat flow. And then we have some local temperature. Then after some time, this local temperature becomes uniform, and the similar thing happens in the in this geometrization, uniformization of geometry. And then this uniformization is described by this so-called Hamilton flow. But there is a problem, actually. In order to define this Hamilton flow, this system must be parabolic. Parabolic means the eigenvalue of this operator must be positive or zero. Positive. Then we can achieve this uniformization. But actually, this Hamilton flow, this operator basically Rich tensor is not a parabolic system, because Rich tensor has, second length tensor, and then there is a symmetry, diffeomorphism symmetry, and then this gauge degrees of freedom correspond to zero mode. So this theory is not well defined because this operator is not completely parabolic. So in order to prove this Thurston conjecture, we have to overcome this problem. And then Perelman did this difficulty. To overcome this difficulty, he introduced new gradient flow. So this is the usual Hamilton flow, but he added this scalar term. And then the corresponding this term can arise as a equation, Einstein equation, if you have this kind of action.
Is this Minkowskian action or you?
This is the Euclidean, but we can also define Lorentzian version. But in mathematicians' interest is Euclidean manifold, 3 manifold. But if you want, we can introduce also Lorentzian version. Well, of course, there is one minor assumption. This in order to have increasing functional, we have to define heat flow using this equation, and then this action should have this property, increasing functional. So Perelman actually introduced this assumption. This time flow of the scalar operator is related to the geometric flow of metric. But Perelman's achievement, he showed that all 8 kinds of Thurston geometries is described by the solution of this equation. Perelman finds an operator, this operator, that vanishes for all Thurston geometries, which satisfy gradient flow. This is called gradient flow, not Hamiltonian flow. Of course, if we just ignore this one, then there is Hamiltonian flow. But if you include scalar field, that is called gradient flow.
Is there any reason for the fact that the scalar f is just like a Dirac term?
Yeah.
So actually, in the first part of your talk, you said that the Einstein-Hilbert action can be converted to the Chern-Simons action, and we have said that the Chern-Simons level k was L over 4G. It should be an integer. And according to the string theory, L over 4G is nothing but the number of D1 ring times the number of D5 ring, which is integer. So is this kind of form? I think that one originates from the mathematicians. But is this related to string theory?
Great. It's actually there is some work. This equation is actually derived from string theory. So Chaplin and some other guys already address these problems. Good question.
So is that thing related to the fact that the gravitational theory might be UV finite, which can be only achieved using the string theory? So is it related to the UV finiteness of relativity?
I'm not sure, but the motivation of introducing this term is, as I already mentioned, this operator is not parabolic. So by including this scalar term, and then although this goes to 0, this term goes to 0, then we have extra term. So we have positive eigenvalue for this operator. Then we can define well-defined uniformization procedure for the 3 geometry. So that is the motivation to including this term. But I don't know. This is related to some UP problem or not.
I mean, this is really string action.
Yeah, string action, right?
So,
Including this,
all these good properties should make things work.
Okay, so then if you know the answer, then let's discuss.
This condition is says that double physics dilaton is T independent.
Oh, okay, then you can address this problem in the DFT. That is also an interesting direction, I think. Okay, so that is my now we are want to find the answer for this question. So how many Thurston geometries can be described by Chern-Simons gauge theory? So Chern-Simons gauge theory, we have freedom of the choice of gauge group and right, only that choice. But as I already pointed out, only three kinds of geometries are Einstein manifold. I mean, the vacuum solution of gravity. That means for other space, we need matter. Then matter is required. Then what are the possible Chern-Simons method theory? We want to describe the Thurston geometry using Chern-Simons gauge theory. Then maybe for some geometries, we need to add matter. Then the question is, what kinds of matter? Okay. So I think, so we need to find Chern-Simons gauge theory of this Perelman section. And then this scala corresponds to matter. And then I want to classify the specific property of this scalar field for given Thurston geometry. And then what is the corresponding two-dimensional conformal filter? Because we have some boundary, then if you believe gauge gravity duality, and then the non-trivial boundary condition may be encoded in the two-dimensional conformal field theory, like Bess-Zumino-Witten and Liouville. And then what is the corresponding two-dimensional conformal field theory of Thurston geometries? And then another question is, so this property, uniformization, there is some universal flow, which becomes, eventually this operator becomes zero. So there is some flow, and this flow direction is very much like entropy direction. And actually,
you don't need cosmology spectrum.
Yeah, if we include this one, we don't need. But I think by collaborate choosing this scalar field, then we can we can have some cosmological constant, because if f is, for example, f is proportional to x, then we have a cosmological constant here. So my another question is what is the actually Perelman introduced Perelman entropy together with previous action, and then this Perelman entropy just describe the plot. I mean the evolution of three geometries, and then I think that there must be some physical interpretation of Perelman entropy. But this entropy will be different from Bekenstein-Hawking, because Bekenstein-Hawking entropy is the black hole solutions, but the most geometry is not related to black hole geometry. Then what is the physical interpretation of Perelman entropy? That's an interesting question.
What is it? Do you have some formula for that entropy?
There is an explicit formula, but I don't remember. If you look at Perelman's second paper, then he introduced this Perelman. After my talk, I will give you, I send you this paper. Of course, we can have many other questions, and then we want to address this question in our ongoing work. And if I have some result, and I will report. Okay. Yeah.
So, can Perelman entropy be applicable for any other geometries? Even though it's not correct.
So, so we start some arbitrary geometry, and then this arbitrary geometry is a flow in some directions where this operator becomes vanishing. So every that means every Thurston geometry is a solution of this equation. The gradient, this operator becomes zero. That means Thurston geometry is a solution of this equation. And underlying action is this one. And this is a very famous action occurring in string theory. So at this stage, I don't have any answer about this question. So I will report later. Okay, thank you for your attention.
Okay. Thank you for the interesting and nice talk. So, actually, we have more time to ask him. So please raise your hand if you have any questions.
Oh,
yeah.
We realize a PTZ black hole in terms of the transcendence theory, because the usual PTZ black hole is not able to point.
Actually, BTZ black hole is the twisting of this ADS2 theory. So I think if we slightly twist this space, then we can realize BTZ black hole. BTZ black hole is a twisting of ADS3. So if there is some identification of ADS3, then we have BTG solution. So I think BTG solution belongs to this class.
But that metric you have shown is not a transcendence, but the usual space-time metric. So in terms of the transcendence theory, how can we write down the state of the BTZ black hole? Because as far as I know, to introduce the BTZ black hole, we have to prepare a free space and make it make a portion of that space, and we have to thermally excite that system. So in terms of string theory, at T1, T5 system or the F1 NS5 system can realize that it is P geometry. But in order to realize a BTZ black hole inside the P geometry, we have to thermally excite the string theory system, like T1, T5-T system, which is thermal excitation. But how can we describe such a thermal excitation in terms of the transcendence theory?
Actually, there is a formulation of in terms of Chern-Simon gauge theory. That is the famous Brown and all. And now it is well known. We have Chern-Simon gauge theory of ADS3, and then we can accommodate this BTG black hole. BTG black hole is actually the solution of this Chern-Simon term. We don't need mu term. And then we have boundary theory. And then this boundary theory has compound field theory, and this compound field theory is described Cardi formula. And the Cardi formula precisely explain Bekenstein-Hawking entropy of BTG black hole. So it is a well-known story, actually.
Now, I also have one more distinct question. In the last part, you have mentioned about the Chern-Simon's method theory.
Yeah.
But that kind of theory used to have some various kinds of soliton called the vortex.
Yeah.
So are they realized in the gravity on the Thurston manifold?
Very good question. Now, so maybe if we just consider this one, then there is some soliton solution already known. Then the question, what is the corresponding geometry? That is a very good question. I don't know the answer, but I think that is a good question. So I will try to find some answer.
So any other questions?
So you showed that you said that this Thurston geometry satisfies the higher curvature action.
Yeah.
You show.
Oh, sorry.
Okay.
Yeah. The solution of this.
Question is that this action is quite special action because
Yeah.
coefficient of each scalar and
Yeah.
then only for that coefficient.
Yeah. So actually, the Townsend and others carefully choose this coupling such that this theory doesn't contain ghost. So unitary theory.
But you said that Thurston geometry is the most general geometry.
Yeah, most general. Yeah.
But they satisfy only this special action?
But Dennis, he considered more general case, more general class of quadratic theory, and they also claim they can accommodate all eight Thurston geometry by this quadratic gravity. But this is the unit. I like this one because this is the unitary theory. No ghosts, but with this modified equation, we can accommodate all Thurston geometry as a vacuum solution. So that is enough to have this unitary theory. But if we just consider general quadratic theory, then unitarity is not guaranteed. It's a bad property. So why we consider non-unitary theory? Or we have this unitary theory, and it is enough to accommodate eight Thurston geometry with this.
What is the connection to Perelman's scalar action?
Sorry?
Connection of this to the Perelman's.
Perelman.
Yeah, Perelman
With
scalar field.
So Perelman's theory is just this one. So Einstein gravity is the usual.
Yeah.
Of course, we contain a scalar field.
Yeah.
That is also a good question. So there must be some relation, right? This theory and then higher order, this one. Yeah, good question. I don't know.